Okay. Okay, with that, let's go on to our next talk then. Next up is going to be Phyllis Klarmann. She's going to be giving a talk on the CERP interim goals for oyster in the northern estuaries using the regional simulation model and habitat suitability indices. Phyllis comes to us from the South Florida Water Management District, and she is a senior scientist with the Applied Science Bureau at the district, and she is a district program manager for Recover. She has a Master's of Science from Florida Atlantic University and several years of academic and professional experience in estuarine ecology and ecosystems restoration and management. So welcome, Phyllis. Take it away.
Good afternoon, and thank you for the introduction. My name is Phyllis Klarmann. I am a senior scientist at the South Florida Water Management District in the Coastal Ecosystems section and the Recover Program Manager for the district. Today, I'll be covering the Recover interim goals for the eastern oyster in the northern estuaries. First, a quick introduction of the Comprehensive Everglades Restoration Plan, or CERP, and its connection to the northern estuaries. As restoration practitioners, you have likely seen this figure before, which captures the historical Everglades flow regime on the left, compared to the current flow regime in the center that resulted from expansive drainage and compartmentalization of the system via a complex network of canals and water control structures. For the northern estuaries, including the St. Lucie estuary on the Atlantic coast and the Caloosahatchee River and estuary on the Gulf Coast of Florida, this includes a connection to Lake Okeechobee that did not historically exist, resulting in the altered volume, timing, and distribution of freshwater inflows, which have an impact on estuarine ecology. When I refer to restoration in the context of these estuaries, I'm referring to salinity as a primary driver of reestablishing a healthy ecosystem, with a focus on reductions of deleterious freshwater inflows during the wet season and providing sufficient base flow during the dry season. The Northern Estuaries module of Recover includes a few different ecological indicator species, which are monitored as part of Recover's monitoring and assessment plan to assess CERP progress. These include the eastern oyster, Chrysostera virginica, as well as the submerged aquatic vegetation community, or SAV community, which includes several species that run the gamut of salinity regimes, including tape grass or Balasneri americana, which is a freshwater or oligohaline adapted SAV, and shoal grass, Haliduli wrightii, which is a mesohaline or more marine adapted SAV. For the purposes of interim goals and interim targets, the only indicator in which we had tools available to simulate interim goals for the northern estuaries includes the eastern oyster, Chrysostera virginica, and so I'll focus on that for today's presentation. The oyster interim goals are based on a Habitat Suitability Index model, or HSI. These models are spatially explicit and fine scale and are used to identify the capacity of a given habitat to support a species of interest. HSI does not predict parameters such as density of oysters, but rather area and acres of suitable habitat, and this is modeled using supportive environmental conditions. More specifically, in our model, we use average salinity, temperature, and available substrate. The supportive habitat being measured is for the purpose of quantifying the value of management alternatives, specifically the current and future scenarios of CERP project implementation here, which was discussed in detail in our introductory presentation by Agnes McLean. As a refresher, we have the existing condition base, which reflects the current system today and will be called ECB IGIT on subsequent slides, and three future scenarios, including 2026, 2032, including the Central Everglades Planning Project, or CEP, and a 2032 scenario that includes CEP and the Everglades Agricultural Area Reservoir and Stormwater Treatment Area, which will be referred to as Run to Packer, or the 2032 scenario in subsequent slides. These RSM basin model outputs include simulated flows in each of these scenarios, and established flow salinity relationships from measured historical data allows us to plug the RSM model results directly into our oyster HSI model. So here are the oyster habitat suitability functions that go into the HSI model formula. HSI scores run from 0 to 1, with a score of 0 being unsuitable habitat and 1 being suitable habitat, which is found on the y-axis of each of these graphs. A salinity of 15 to 25, temperature 23 to 30 degrees Celsius, and substrate with available shell was deemed most suitable with a score of 1, with higher and lower salinity and temperature, or other substrate classifications from an Oyster mapping event from 2019, resulting in lower HSI scores. Here's an example of how the individual functions are brought together to create a GIS-based composite HSI map. Here we have a salinity layer, a temperature layer, and an available substrate layer. And these come together to form the composite HSI map, which reflects polygons that are color-coded based on HSI scores. And these HSI scores are grouped as either poor, fair, good, or very good, based on the following ranges of those scores presented here. Now, before I show you the HSI results, I first want to go into some results of the simulated futures and the hydrologic change that is expected. Flow outputs from the RSM basins model demonstrate that with each future CERP scenario compared to the existing condition base, the percent of time that mean monthly flows fall within the stressful and damaging flow thresholds in the St. Lucie estuary on the left and the Caloosahatchee estuary on the right decrease. However, we're not quite meeting a desired restoration hydrologic condition as indicated to the right of each set of bars here for the St. Lucie in blue, and here for the Caloosahatchee, which is indicative of 0% of the time. But the good news is that improved hydrologic conditions presented here are indicative of benefits from CERP project implementation, namely additional storage south of Lake Okeechobee. And you'll see the benefits of these reduced high flow scenarios in the following HSI maps. So first, the results for the St. Lucie estuary. Here you'll see two maps. On the left here, this is the oyster habitat suitability measured in the existing condition-based scenario. And on the right is the 2032 future scenario. As indicated in the legend, darker colors are poor or fair habitat, and lighter colors are good or very good habitat. Greatest improvement that we see in the St. Lucie estuary with the 2032 future scenario, an improvement in habitat suitability in the North Fork and the South Fork of the St. Lucie estuary, where usually we see the greatest impact of damaging high inflows. So the future increases in habitat suitability are likely a result of improving salinity conditions. The increase in acres of oyster habitat that receive good and very good HSI scores improve with each future scenario, but especially with that 2032 Packer scenario. And here you will see the totals of each HSI category across the scenarios modeled, with good and very good habitat, again, increasing with each future condition. For results for the Caloosahatchee estuary, here is a zoomed in map of the lower reaches of the Caloosahatchee. So just to orient you with some geographical locations, out here is San Carlos Bay. The lower estuary is here from Shell Point. And then as you work your way upstream, Cape Coral is just slightly off the map here. Again, on top, we have the existing condition base HSI, and on the bottom, the 2032 HSI. So we see similar trends where the habitat suitability categories of good and very good habitat increase with each future iteration. However, the majority of the difference takes place in this area downstream of Cape Coral and upstream of Shell Point, indicated by this black box. This is likely due to the tidal influence and flushing in the lower estuary with proximity to the bay and the Gulf of Mexico. And in the 2019 oyster map, we found no available shell substrate upstream of Cape Coral, and so it was limited to this area here. Again, here you will see the totals of each HSI category across the scenarios modeled, with good and very good habitat increasing with each subsequent future condition. So some takeaways and key findings from the 2032 scenario, again, which includes that EA reservoir and STA, includes a total of 329 acres of good and very good habitat in the St. Lucie and 732 acres in the Caloosahatchee. Now, this is a reminder for all of us that while we did see these improved habitat conditions, hydrologic goals have not yet been attained, and this is a reminder that CERP alone is not the be-all end-all of Everglades restoration, and that additional projects to manage local basin runoff will be needed to reach desired restoration goals in addition to future CERP project components. Finally, with respect to the Oyster HSI model employed, the interim goals are constrained by substrate habitat suitability classifications. So here I've brought up on the screen again the habitat suitability functions I showed earlier. Both salinity and temperature data include data from the full period of record, 1965 to 2005. But in this model, the substrate remains static or unchanging and represents that oyster mapping event I mentioned from 2019. So as reflected in this figure here, which shows an approximately 25-acre patch of oyster reef in the North Fork of the St. Lucie Estuary, you see that over time, with each future scenario, the lower half of the reef habitat improves with each future CERP iteration and changes from fair to good, likely as a result of improving salinity conditions. However, the uppermost part of the reef area remains unchanged for habitat suitability score. And this is despite the improved habitat conditions from improved salinities. And this is because this area of the reef in the 2019 map were designated as lower quality substrate. So the HSI model is not taking into account, one, that reef growth, increasing density, and or an expansion of reef is possible, which we may observe if the salinities become suitable over time, or two, that other restoration measures, including mulch deployment, expected to take place as part of the Indian River Lagoon South project is included. So this supports what we already know, that additional habitat restoration via mulch deployment or other activities will be important for increasing the total area of oysters in the St. Lucie Estuary and will be a useful adaptive management strategy if we don't meet goals moving forward. So finally, just to wrap up for future steps and general findings for Northern Estuaries and term goals. While the Oyster HSI model was the best tool available at the time, more complex mechanistic models that can be paired with the regional simulation model are needed for all Northern Estuaries indicator species, not just oysters. As represented here on the right, you can see an example from Bazzelli et al. What a more complex model would look like. These mechanistic models can be used to update restoration goals and applied to develop both evaluation performance measures, as was done in this exercise, comparing current and future scenario simulations, and assessment performance measures to track restoration outcomes through Recover's ecological monitoring efforts. Finally, with the next interim goals and term targets report expected in 5 years, this will include additional CERP project components as well as updated operational plans, such as the Lake Okeechobee System Operating Manual effort, which is ongoing currently. And with these future projects and with things like LOSM, with the operating manual, we will expect additional benefits to estuarine ecology in the Northern Estuaries. And with that, I would be happy to take any questions.
Okay, Phyllis, it looks like you already answered a couple of the questions, but did you want to just reiterate your question on where the temperature and salinity data come from?
Yeah, so Laura DeCunto and Sarah Hayter had asked where that data came from. So with the salinity, the RSM model, as I mentioned before, generates flow outputs in each of those time steps. So for the existing base and each of the futures. And in developing the HSI model, we were able to develop and using observed flow data, a flow to salinity relationship so that we can generate, once we generate the RSM model outputs of flow, that gets plugged into our HSI model and it gives us salinity. So those are simulated based on this algorithm. And my colleague Zichen, who worked on that, would have to speak to the details of how that algorithm is put together, but I'll leave that for another time. And then the temperature is based on historically measured data. So my understanding is that the temperature is not simulated. It's just a reflection of the period of record. And both of these are then averaged for each time step to generate the HSI maps. And related to the temperature question, I see Lynn Wingard in the chat asked about any plans to run with increasing temperatures as predicted by IPCC. So CERP as a program is trying to develop methods to incorporate climate models. including temperature as well as sea level rise to our projects. But so far, this has only been on a specific project level basis. And hopefully forthcoming, the RSM will be able to incorporate these additional components, because obviously if we're just using a 50-year period of record, that doesn't reflect a future scenario in which we may see increasing temperature or rising sea levels, right? So I agree that those things should be included. I will ask you to just kind of wait and see how we do in the next few years, and you know, I agree that it's something that's needed to evaluate future scenarios. So we'll have to, like I said, just wait and see. And thank you.
Thanks, Phyllis. Okay, we'll go ahead and get started with the